All right. So in the last class, I introduced to you circular motion. And more specifically, I introduced to you polar coordinates in the last class. All right. हम थोड़ा सा slow जा रहे हैं. We are going a little bit slow because these are the initial classes, but I'm going to start picking up pace, huh? I hope that everyone is sort of keeping up with the classes and yeah, थोड़ा सा हम pace pick up करेंगे because we have to finish the syllabus by around mechanics का syllabus by around February है, March, April, May तक तो ख़त्म करना ही पड़ेगा हमें, right? So in the last class, I gave you an introduction to polar coordinates, right? And I gave you a sort of a relationship for certain physical quantities in polar coordinates. For example, position vector, velocity vector, acceleration vector, all these things, right? And I showed you that when we write the various physical quantities, when we change the coordinate system, the expressions are slightly different. So for example, in the velocity vector quantity, there is something called radial speed, which is the component along the radial direction, and transverse speed, which is the component along the transverse direction. That is not strictly equal to r dot and theta dot respectively. Similarly, when we talked about the acceleration vector, there is something called the radial acceleration, which is the acceleration component along the radial direction, and the transverse acceleration, which is the acceleration component along the transverse direction, which is not strictly r double dot and theta double dot respectively, right? So therefore, it is important for us to sort of remember. So keep it in our memory. आप लोग को ये याद करना पड़ेगा. ये थोड़ा सा आपको फॉर्मूला शीट में रखना पड़ेगा, टाइम टू टाइम रिवाइज करना पड़ेगा, so that you have it etched in your memory. You never forget it because these are very important expressions, not just for JAM but in general. आप कभी भी मैकेनिक्स का कोई भी पेपर देते हो तो वहाँ पे स्फेरिकल कोऑर्डिनेट्स या पोलर कोऑर्डिनेट्स से रिलेटेड कोई ना कोई क्वेश्चन आने की संभावना हमेशा होती है. अभी रिसेंटली एक पेपर हुआ था CSIR-NET का, जो लास्ट पेपर था, नेट का पेपर है, सेंट्रल फोर्सेस का क्वेश्चन था. सेंट्रल फोर्सेस के क्वेश्चन में दे हैड दिस टर्म डी आर कैप अपॉन डी टी. मैं अभी रिविजन क्लासेस ले रहा था नेट के बच्चों का, तो उन रिविजन क्लासेस में वी हैड टू डिस्कस हाउ टू रिजॉल्व डी आर कैप अपॉन डी टी. यूजुअली क्या होता है नेट वगैरह में, स्टूडेंट्स जो है दे आर मोर फोकस्ड ऑन लेग्रेंजियन फॉर्मुलेशन, हैमिल्टोनियन फॉर्मुलेशन, ऑल दीज टॉपिक्स. तो बेसिक चीज़ें भूल जाते हैं, जो बहुत ही ज़्यादा बेसिक चीज़ें होती है. बट इवन दो इट इज़ अ नेट पेपर, और नेट में जो पेपर होता है उसमें कुछ क्वेश्चन होते हैं 3.5 मार्क्स के, कुछ क्वेश्चन होते हैं 5 मार्क्स के. तो ये 5 मार्क का क्वेश्चन था जिसमें एक पर्टिकुलर एक्सप्रेशन को सिंप्लीफाई करना था, और उसमें ये पर्टिकुलर एक्सप्रेशन था, ठीक है, और उसमें एग्जैक्टली हमें ये यूज़ करना था, ये वाला एक्सप्रेशन, ठीक है. तो मैंने कल या परसों बैठ करके ये दोबारा से नेट के क्लास में डिराइव किया, क्योंकि नेट के क्लास में क्या होता है, वी यूजुअली सॉर्ट ऑफ बेसिक्स में हम इतना फोकस नहीं करते हैं. हम क्लासिकल लेग्रांजियन, ऑयलर लेग्रांजियन फॉर्मुलेशन, हैमिल्टोनियन फॉर्मुलेशन में ज़्यादा हम टाइम स्पेंड करते हैं बिकॉज दैट इज़ द मेन फोकस. So what I'm trying to say is that these concepts are very sort of important as long as you keep on studying mechanics at any stage. चाहे आप गेट का एग्ज़ाम दो, चाहे MSc में क्लासिकल पढ़ो, चाहे आप नेट का एग्ज़ाम दो, फ्यूचर में कभी आप UPSC के लिए प्रिपेयर करोगे, वहाँ पे फिजिक्स ऑप्शनल चूज़ कर लिया, हर जगह मैकेनिक्स से रिलेटेड कुछ कॉन्सेप्ट्स बहुत ज़रूरी होते हैं, एंड दिस इज़ लाइक वन ऑफ दोज कॉन्सेप्ट्स, ठीक है. नाउ एज फार एज क्वेश्चंस आर कंसर्न्ड, व्हाट काइंड ऑफ क्वेश्चंस कैन वी गेट फ्रॉम सर्कुलर मोशन, फ्रॉम पोलर कोऑर्डिनेट्स? बहुत तरीके के क्वेश्चन हो सकते हैं. आज मैं एक ही तरीके के क्वेश्चन में फोकस रखूंगा अपना. मेरा फोकस आज होगा फ्री बॉडी डायग्राम्स, ठीक है, बिकॉज यही हम डिस्कस कर रहे थे सिंस द वेरी फर्स्ट क्लास. आई हैव बीन ट्राइंग टू फिगर आउट हाउ टू सॉल्व प्रॉब्लम्स by looking at the various forces involved, and based on the various forces involved, what conclusions can we make about the nature of the motion, equilibrium वगैरह वगैरह, by drawing diagrams and drawing arrows in the form of force vector जहाँ पे भी है. तो फ्री बॉडी डायग्राम से रिलेटेड जो सर्कुलर मोशन के प्रॉब्लम है, मैं आज उन्हीं पे फोकस करूंगा, ठीक है। ऑल राइट, नाउ again, in the very second lecture, I gave you some list of instructions, if you remember. Instructions related to how to solve free body diagram related problems. Everything is going to remain the same. सब कुछ सेम ही रहेगा. The only difference is that यहाँ पे point number 3, I said that choose the correct coordinate system. So till now we were only choosing the rectangular coordinate system, the Cartesian coordinate system. So now for today's class we are going to choose the polar coordinate system for specifically motion constraint to a plane or a circular motion. Okay. So free body diagram related problems. Free body diagram related problems involving circular motion. Most of the instructions will remain the same from previous. I will give you some additional instructions. क्या चीज कि पहले हम क्या करते थे, we would choose a XY coordinate system and then we would try to resolve the forces along the XY coordinate system. If you see here, if I have a certain number of forces in a given system and I make a choice of a coordinate system that is XY, तो मैं उन सारे forces को X और Y में resolve करने की कोशिश करता हूँ. It makes our job easier to look at the balancing of forces or the net force equation. But if I do not do the problem in Cartesian coordinates, if instead I do the problem in polar coordinates, then I don't resolve in XY. Then I resolve along r cap and theta cap. Same goes for cylindrical coordinates, spherical coordinates, etc. etc. Okay? So once I make a choice of polar coordinates, I will resolve the various forces along the polar coordinate axes, which is r cap and theta cap. And that is what's important for us. That I want to make this resolution of the forces along the radial and the tangential directions. So resolve all forces along respective radial and tangential directions. Okay, you have radial direction and you have tangential direction. But the question is, once you resolve the forces along radial and tangential directions, how do you write the force equations? Because if there are imbalanced forces or net forces, I need to write the force equations. If you remember from my previous class, I have derived the acceleration expression. And finally, I gave you these two expressions. These two expressions are very important. Okay, Fr is the forces along the radial direction. F theta is the forces along the transverse direction. So these two are the force equations. Okay. And you have to keep in mind कि इसी को हमें use करना है, कोई दूसरा नहीं use करना. So Fr is equal to m r double dot minus r theta dot square, and F theta is equal to m r theta double dot plus 2r dot theta dot. Very important. ठीक है? For some students, this equation may look a little complicated, but your life will become very easy if you memorize them. Okay, there is no other way. This is the easiest step actually. Just memorize it, and whenever you have unbalanced forces along the radial direction, apply the first equation, and whenever you have unbalanced forces along the tangential direction or the transverse direction, apply the second equation. Okay. And in some cases, it might be helpful to consider an additional concept called vertical equilibrium. Vertical equilibrium. Okay. So let us take a couple of case studies and study this problem. Vertical equilibrium case studies. So case study number 1. Simple pendulum. Simple pendulum is one of the very simple examples of circular motion because you have a bob which is hanging from a wire suspended on a ceiling, and if you release it in the presence of acceleration due to gravity, it is simply oscillating back and forth on the arc of a circle, right? And in fact, just give me a so if you have a simple pendulum problem, so this is the theta, all right. This is your radial direction, outward radial direction. The outward radial direction is a positive direction, okay? जैसे x और y में we have positive and negative, उसी तरीके से the outward radial direction is your positive r cap, and the outward transverse direction जहाँ पे theta is increasing is your positive theta cap. ठीक है? The positive and negative is important because whether you take a force to be in the positive direction and negative direction makes sense only from the perspective of a axis. तो एक्सिस में अगर आप सही लोगे तो आपका वो पॉजिटिव नेगेटिव सही होगा, नहीं तो सारा कुछ गलत हो जाएगा. ठीक है? सो थीटा कैप इज पॉजिटिव इन द आउटवर्ड डायरेक्शन जहां पे थीटा इज इंक्रीजिंग, ऑलराइट, एंड r cap is all positive in the outward direction jahan pe r cap is increasing. Okay, now this is our system which is sort of experiencing motion on the arc of a circle. What are the various forces involved? So it is kind of clear that if there is a point mass here, the simplest force is the force of gravity, which is mg. This angle is also theta. So if I want to resolve, and of course the second force is the tension. So if I want to resolve this gravitational force, how can I resolve it? Number one, I can resolve it along the direction of the radial vector. So this is going to become mg cos theta, and I will also direct it in the perpendicular to the radial vector, which is mg sin theta. ठीक है? And of course there is tension, and this is basically R is equal to L वगैरह वगैरह. All right. So because we are dealing with a simple pendulum problem where r is a constant, है ना? So I want to write down the various force equations. So what is a force equation along radial direction? The force equation is already given to us. Fr is equal to m r double dot minus r theta dot square. ये force equation है by definition for any problem. So the question is, what is Fr? What is Fr, guys? What is the net unbalanced force along the radial direction?
T minus mg cos theta.
T minus mg cos theta. देखिए, this is a very simple mistake that you have made, but that is really going to cause trouble in the further calculations. Because अभी मैंने थोड़ी देर पहले आपको बताया था that whether you make a force positive or negative depends upon the direction of the axis, and the axis is positive only in a specific direction. And I've made it very clear that outward radial is positive and the outward transverse is positive. ठीक है? Now, of course, if you make two mistakes in both the directions, your answer will come out to be the same. But if you make a single mistake, एक plus minus का दिक्कत हो जाएगा आपको. ठीक है? So we want to avoid those silly mistakes. So therefore, अब मुझे बताइए, if the outward radial is the positive axis, then the net force will be how much?
mg cos theta minus t.
Very good. See, the thing is, it's not a big thing. It's a very small thing. But इससे क्या होगा? बहुत सारी गलतियां avoid हो जाएंगी. Many silly mistakes will be avoided. Okay. So I'm going to write it in the positive x-axis by keeping the positive r-axis as the direction where the forces, net force I'm looking for. So mg cos theta minus t. Okay, I hope that everybody understands this, because this is a very common mistake and we want to avoid it. So this is equal to, because r is a constant, therefore r dot is equal to r double dot is equal to 0. तो ये बन जाएगा minus mr theta dot square. That's it. So therefore I can rewrite this equation as t is equal to mg cos theta plus mr theta dot square. So this is one of the equations for the simple pendulum, okay, especially along the radial direction. Of course, I can simplify it, because you know that theta dot is what? Theta dot is nothing but omega, right? And this is purely circular motion. आप लोग को याद होगा from my previous class that I said for purely circular motion, V is equal to omega r or omega L, right? So that means theta dot is equal to omega is equal to V upon L. So therefore, this can also be written as T is equal to mg cos theta plus r or L m V square upon L. Okay? Let me consider this as equation number 1. Right now, I'm not trying to solve a problem. Right now, I'm simply giving you the various force equations along the various direction, so that depending upon the question, you can use them. So if you look at the JAM papers, they might ask you all kinds of questions. We'll see a couple of them. तो यहाँ वहाँ पे आप यूज कर सकते हो, इसलिए मैंने आपको डिराइव करके ये दिखा दिया है. Now, if I do the same thing along the transverse direction, transverse direction में क्या होगा? Transverse or tangential direction. So I'll write the original force equation. So original force equation is F theta is equal to m r theta double dot plus 2 r dot theta dot. Of course, r dot is equal to 0, तो एक ही expression बचता है, which is m r theta double dot. So what is the force in the net force in the transverse direction? बताइए।
माइनस एम जी
साइन थीटा।
करेक्ट, वेरी गुड। माइनस एम जी साइन थीटा। ये माइनस बहुत ही इंपॉर्टेंट है, क्योंकि अगर मैं माइनस नहीं लगाऊंगा तो मेरा जो डिफरेंशियल इक्वेशन का सॉल्यूशन कुछ और आ जाएगा, माइनस लगाऊंगा तो कुछ और आ जाएगा। इट्स वेरी इंपॉर्टेंट, यू विल सी। ओके, सो व्हाट इज दिस? दिस इज एसेंशियली, आर को हम एल लिख सकते हैं, आर इज इक्वल टू एल। सो दिस एसेंशियली बिकम्स d2 theta upon dt2 is equal to m, and m gets cancelled, और ये प्लस g upon l sin theta is equal to 0. What is this? This is the equation of motion of the simple pendulum in terms of its angular displacement. This is the equation of motion of the simple pendulum. That's it. ये simple pendulum का equation of motion है. The question is, can I solve it? Has anybody solved this equation of motion?
Yes, sir. But not really. If we take the small angle approximation, then it can be solved.
Yes. The thing about a simple pendulum is that it is not that simple. Why? Because we don't really solve for the pendulum. We only solve for a very special case, जिसको हम कहते हैं small angle approximations. I have a question in the chat. Question, so there's one doubt, mg cos theta minus t should be 0 since the pendulum ball isn't going radially outwards. No, no, it's circular motion. See, Kashan, there is a net force along the radial direction. There is a net force. जरूरी नहीं है that the net force causes radial motion. Are you understanding? How do I explain it?
नो सर, मतलब यही समझ में नहीं आ रहा। मतलब वो बॉल बाहर जानी चाहिए ना, मतलब रेडियली हो।
नो, देखिए क्या होता है कि देखिए जो लीनियर मोशन होता है ना, उसको समझना थोड़ा आसान होता है, लेकिन जब सर्कुलर मोशन होती है ना, थोड़े से कुछ चेंजेस आ जाते हैं। सो फॉर एग्जांपल, आपको पता है कि अगर कोई ऑब्जेक्ट सर्कुलर मोशन में है, अगर उसकी वेलोसिटी कांस्टेंट है, तो क्या उसकी एक्सेलरेशन जीरो होगी? बताओ।
सर अगर स्पीड कांस्टेंट है और डायरेक्शन चेंज हो रही है तो फिर जीरो नहीं होगी।
तो अगर एक्सेलरेशन नॉन जीरो है तो फोर्स भी नॉन जीरो होगा।
यस सर।
वही तो है ये। आर यू अंडरस्टैंडिंग?
यस
ये
सर।
किसी भी तरीके का सर्कुलर ऑर्बिट के लिए होगा। फॉर एग्जाम्पल, व्हेन वी टॉक अबाउट द मून्स मोशन अराउंड द अर्थ, वहां पे भी है। देखिए आप लोग क्या करते थे, मैं बताता हूँ। स्कूल के टाइम पे आप लोग करते थे कि नीचे की तरफ एक फोर्स लगाते थे, ग्रेविटेशनल फोर्स, ऊपर की तरफ एक फोर्स लगाते थे, सेंट्रीफ्यूगल फोर्स, और दोनों को बैलेंस कर देते थे। ठीक है, दैट इज द वेरी सॉर्ट ऑफ सिंपल वे ऑफ लुकिंग एट बैलेंसिंग ऑफ फोर्सेस इन सर्कुलर मोशन। ठीक है, पहले आप ये करते थे कि सर्कुलर मोशन में अगर कुछ हो रहा है तो अलोंग द रेडियल डायरेक्शन में ग्रेविटी लगा देता हूँ, अगेंस्ट इट में सेंट्रीफ्यूगल फोर्स लगा देता हूँ। करते थे ना आप लोग? करते थे, है ना? लेकिन अभी जो ये सेंट्रीफ्यूगल फोर्स है वो ऑटोमेटिकली इक्वेशन में आ गया। कैसे? मैंने तो लगाया नहीं अपने अलग तरीके से। इट इज पार्ट ऑफ द फोर्स इक्वेशन। एनी टाइम समथिंग इज मूविंग इन अ सर्कुलर मोशन, तो एक रेडियल कंपोनेंट ऑफ फोर्स होता ही होता है। रेडियल कंपोनेंट ऑफ फोर्स अगर नहीं होगा ना, तो सर्कुलर मोशन करेगा ही नहीं। अब बात को समझो। मैं अगर एक छोटा सा पत्थर पकड़ लेता हूं, उसको रस्सी से बांध देता हूं और ऐसे घुमाता हूं, ठीक है, तो रस्सी का जो टेंशन है ना, उस बॉल को सर्कुलर मोशन बना करवा रही है। वो अगर रस्सी टूट जाएगा तो द बॉल विल गो अलोंग इन अ टेंजेंट इन अ स्ट्रेट लाइन, है कि नहीं? यस।
यस सर।
That means there is a force which is causing the change in the path. तो यहां पे आप ऐसे सोच सकते हो कि ये जो रेडियल फोर्स है ना, दैट इज एक्चुअली कॉजिंग द सर्कुलर मोशन एक तरीके से। मतलब आप इसको ऐसे सोच रहे हो कि नहीं, दोनों तरफ तो बैलेंस होना चाहिए क्योंकि वो रेडियल रेडियल रेडियस कांस्टेंट है, बट देयर इज अ नेट फोर्स दैट इज कॉजिंग द सर्कुलर मोशन। क्योंकि अगर हम इसको ऐसे फ्रीली छोड़ देंगे ना, तो इट विल मूव इन अ टेंजेंट। फ्रीली अगर मैं किसी चीज को छोड़ दूं तो वो इट विल मूव इन अ टेंजेंट, इट विल नॉट मूव इन अ सर्कुलर पाथ। नेचर में अगर हम देखें ना, न्यूटन्स फर्स्ट लॉ ये नहीं कहती है दैट ऑब्जेक्ट्स हैव अ टेंडेंसी टू मूव इन अ सर्कुलर पाथ। नहीं, ऐसा नहीं कहती है। न्यूटन्स फर्स्ट लॉ कहती है दैट ऑब्जेक्ट्स हैव अ टेंडेंसी टू मूव इन अ स्ट्रेट लाइन। तो ऑब्जेक्ट्स हैज अ टेंडेंसी टू गो इन अ स्ट्रेट लाइन, नॉट इन अ सर्कुलर पाथ। तो सर्कुलर पाथ में मूव कराने के लिए एक फोर्स की जरूरत होती है ना? आप अगर वो जो बच्चों के खिलौने होते हैं जहाँ पे छोटे छोटे कार होते हैं जो ऐसे करके हुम करके ऐसे करके चला जाता है इन कर्व्ड दिस थिंग, तो वो कर्व में ऐसे क्यों जाता है? बिकॉज देर इज अ सर्टन अमाउंट ऑफ वेलोसिटी दैट कॉजेज अ सर्टन काइंड ऑफ अ सेंट्रीफ्यूगल फोर्स, और उसका एक नॉर्मल रिएक्शन होता है। बिकॉज ऑफ दैट रीजन इट गोज इन अ सर्कुलर पाथ। सो यू डू नीड अ फोर्स टू कॉज समथिंग टू गो इन अ सर्कुलर पाथ। आर यू अंडरस्टैंडिंग?
यस
सो
सर।
देयर इज गोइंग टू बी अ नेट फोर्स। मतलब इस चीज को थोड़ा समझाना मुश्किल है, बट द मोमेंट यू हैव अ पार्टिकल विच इज चेंजिंग इन डायरेक्शन, सर्कुलर पाथ में क्या होता है, डायरेक्शन इज कॉन्स्टेंटली चेंजिंग, ऐसे ऐसे करके चेंज हो रहा है, ठीक है? तो देयर इज अ नेट फोर्स दैट इज नॉट ऑब्वियस इफ यू कंपेयर विथ एन एक्स वाई प्लेन। एक्स वाई प्लेन में क्या होता है कि अगर कोई ऑब्जेक्ट एक ही पर्टिकुलर प्लेन में होता है तो परपेंडिकुलर डायरेक्शन में फोर्सेस आर बैलेंस्ड, एंड दैट इज करेक्ट। दैट इज करेक्ट बिकॉज ऑफ न्यूटन्स फर्स्ट लॉ। न्यूटन्स फर्स्ट लॉ कहती है ऑब्जेक्ट विल मूव इन अ स्ट्रेट लाइन अगर कोई फोर्स नहीं लगे तो। लेकिन यहाँ पे ऑब्जेक्ट इज नॉट मूविंग इन अ स्ट्रेट लाइन, इज मूविंग इन अ कर्व पाथ। तो कर्व पाथ में मूव करने के लिए इट रिक्वायर्स अ नेट फोर्स। ओके, ऑल राइट। नाउ इफ आई वांट टू अंडरस्टैंड, हाँ, इफ आई वांट टू अंडरस्टैंड कि ये क्या है इक्वेशन ऑफ मोशन, तो सारे पेंडुलम्स का जो ये एक इक्वेशन ऑफ मोशन होता है, बट द प्रॉब्लम इज दैट दिस इज this is not a harmonic oscillator. आप लोग को पता है SHM क्या होता है? यू नो व्हाट इज सिंपल हार्मोनिक मोशन? पता है? एनीबडी नोस व्हाट इज SHM?
This simple means we are taking a special case here, but harmonic oscillator means it it is a oscillator with a certain time period.
Harmonic oscillator means it has a potential energy which is perpendicular to
The length
theta
of the
square. Theta square. It's a parabola. See, oscillator is not a harmonic oscillator. Oscillator और हार्मोनिक ऑसिलेटर में फर्क होता है। हार्मोनिक ऑसिलेटर वो होता है जिसका मोशन साइनोसॉइडल होता है। ऑसिलेटर कुछ भी हो सकता है, ऑसिलेटर साइनोसॉइडल नहीं भी हो सकता है। ऑसिलेटर में बैक एंड फोर्थ मोशन की जरूरत है, ऑसिलेट करने की जरूरत है। हार्मोनिक ऑसिलेटर का मतलब होता है साइनोसॉइडल फंक्शन। पोटेंशियल एनर्जी कर्व इज अ प्रोपोर्शनल टू थीटा स्क्वायर, इट्स अ पैराबोला पोटेंशियल एनर्जी कर्व। सो व्हाट इज सिंपल हार्मोनिक मोशन?
सर जो हुक्स लॉ के अकॉर्डिंग होता।
तो क्या पेंडुलम हुक्स लॉ के अकॉर्डिंग होता है? नहीं होता है। पेंडुलम इज नॉट एन एग्जाम्पल ऑफ अ हार्मोनिक ऑसिलेटर। पेंडुलम का जनरल मोशन इज नॉट अ सिंपल हार्मोनिक ऑसिलेशंस। नाउ यू कैन से अरे ये कैसी बात हो गई, हम तो स्कूल के टाइम से यही पढ़ते हैं आ रहे कि सिंपल पेंडुलम का जो मोशन होता है वो SHM होता है, साइनोसॉइडल मोशन होता है। पढ़ा कि नहीं आप लोगों ने? स्कूल के टाइम
Yes,
में
sir.
पढ़ा होगा, कॉलेज के टाइम पे मैकेनिक्स के क्लासेस में यू मस्ट हैव डन लैब and your teacher might have asked you to do the simple pendulum problem or a bar pendulum problem or a Cater's pendulum problem, right? Or some kind of a Maxwell's needle problem. So many problems are there which are based on oscillations. Maxwell's needle to thoda alag ho gaya. Now there the teacher gives you an instruction. Teacher tells you, please make sure that the amplitude is very less. बोला होगा. Anytime you did a pendulum problem, whether in class 12th or in college, your instructor would have told you, make sure that the amplitude is less. अगर एम्पलीट्यूड आपने ज़्यादा कर दिया, ऐसे ऐसे ऑसिलेट कर रहा हो, टीचर ने आके बोला होगा नहीं, इतना ऑसिलेट नहीं करना, 5 डिग्रीज या 10 डिग्रीज, इससे ज़्यादा नहीं करना. बोला है? हैज़ एनीबडी बीन गिवन दिस इंस्ट्रक्शन बिफोर?
Master, angle should be small. My instructor told like this.
Pardon?
The sine angle should be small. The oscillating.
Yes. Why have they given you this instruction? Any idea?
So that
Small
we can
approximation.
use the formula used to E is equal to 2 pi under root L by J. Otherwise, if the amplitude is very large, so we can't use the formula there.
Yes, correct. So if I make that assumption that amplitude is very small, which is also called as small angle approximation, then what is sine theta? Sine theta is approximately equal to theta. This is the approximation. They told you amplitude should be low. Why? So that sine theta is approximately equal to theta. Why? Because now the equation of motion becomes d2 theta upon dt2 plus g upon L, theta is equal to 0. You guys have studied mathematical physics. Do you know the standard solution of some equation like d2y upon dx2 plus k square y is equal to 0? Do you guys know the standard solution of
Yes,
this kind
sir.
of a differential equation? What is it?
Yes, sir.
A e to the power I omega t, I k t plus a b e to the power minus I.
That is a
Yes.
complex solution, the general solution. If I,
A sin omega t plus b cos omega t, like this.
so y is equal to a sine kx plus b cos kx, because I've written it in terms. This is a standard solution, yes? See, in physics, in mechanics, in quantum mechanics, in statistical physics, in EMT, there are a lot of differential equations, and sometimes you will have to use standard differential equations, and many times certain differential equations keep coming up over and over and over again. So this is one of the most famous differential equations out there. You will see this differential equation right now in mechanics related problems, as well as later on when we study quantum mechanics. There also you will see this differential equation many times. So इसको आप याद रख लो. कहीं पे भी इस तरह का differential equation आ जाता है, तो you will get a solution like this. Now depends whether the solution should be real or complex. If like in quantum mechanics we want a complex solution, तो वहां पे आपने जो पहले बताया e to the power iota kx, वो वाला solution आ जाएगा. But right now I want a real solution. तो real solution के लिए ये है real solution. ठीक है? So therefore, what is the solution here? Theta t is equal to, so let's suppose omega square is equal to g upon L. So here we have omega square. So I think it is case. So theta t is equal to a sine omega t plus b cos omega t. All right. There is another way of writing this same solution. It's a sum of sines and cosines. दो तरीके हैं इसको लिखने का. There is another way of writing it. We can also write it as c cos omega t plus phi. Both are same. पता है ना आपको? These are both same. A and B and C are constants. दोनों equivalent है. Yes?
Yes,
Both
sir.
are, yeah, both
Yes,
are
sir.
equivalent. Both are equivalent because यहाँ पे cos A plus B is equal to sin A cos B plus cos A sin B. So both are equivalent. So if I take initial conditions, for example, if I say, okay, initial conditions, that initially at time t is equal to 0, theta is equal to theta naught, then your particular solution is going to be theta t is equal to theta naught cos omega t. Okay, which is what It is a simple harmonic oscillation. So this is t, this is theta, that's it. It's a cosine function. So then this becomes a SHM. And this represents small angle approximation creates a harmonic oscillator. So यहाँ पे मैंने आपको बहुत सारा इंफॉर्मेशन दे दिया है जो जरूरी नहीं है जैम के पर्सपेक्टिव से, but in general it makes it interesting that a pendulum is not a harmonic oscillator. It doesn't execute SHM for large angles, but for small angles it becomes a harmonic oscillator and it starts executing SHM for small angles. So pendulum is a very peculiar example of a harmonic oscillator. The standard example is a spring mass system. Spring mass system is a standard example of a harmonic oscillator. Pendulum is not a harmonic oscillator for large angles, but for small angles it behaves like a harmonic oscillator. It's a very interesting problem. ठीक है, मैं pendulum को study नहीं करना चाहता था. I was just showing you the steps involved in studying any mechanical system which is causing circular motion. So I hope that these steps have given you some idea of how to proceed in a problem. बताइए, is it clear? Do you have any doubts?
Sir, harmonic oscillator have to be sinusoidal or can it be any other function?
What other function?
I mean, like a square wave function, any function having a. Oh, okay.
Any using any periodic function?
Yes.
Sinusoidal. Harmonics है ना? Harmonics में you usually deal with sinusoidal function. But बाद में आप पढ़ोगे second year में, third year में, when you study Fourier series, that any periodic function can be decomposed into a large number of sinusoidal functions. So essentially any kind of a periodic function can be made up of a summation of sinusoidal waves. So a harmonic oscillator is something that contains a single sine wave. But there are certain physical systems in our universe जिसको हम बोलते हैं coupled oscillator. They contain multiple sine waves. So वहां पे sine waves का sum हो जाता है. तो sine waves के sum के बाद भी एक periodic function आता है. उनको आप harmonic oscillator नहीं बोलते हैं, coupled oscillator बोलते हैं. बट अगर स्ट्रिक्टली आप पूछोगे कि हार्मोनिक ऑसिलेटर का सोल्यूशन क्या है, इट इज अ साइनोसॉइडल वेव. लेकिन अगर आप ये बोलोगे कि मेरे पास अगर कोई पीरियोडिक फंक्शन है, क्या उसको मैं हार्मोनिक ऑसिलेटर बोलूंगा? नो, इट्स नॉट अ हार्मोनिक ऑसिलेटर स्ट्रिक्टली स्पीकिंग, बट इट कैन बी डिकम्पोज्ड इनटू अ लार्ज नंबर ऑफ हार्मोनिक्स. ठीक है, आप म्यूजिक सुनते हो तो उसमें बहुत सारे फ्रीक्वेंसीज प्रेजेंट होते हैं ना, दे ऑल गेट एडेड टुगेदर.
Sir, in usual case, day-to-day life, simple when during experiment, the simple pendulum eventually comes to rest. So there is certain amount of damping that is involved. So how can we uh, introduce that damping into this framework? Is there any way to do that? Like we have assumed that sine theta is equals to theta for small angles. So means how can we introduce damping?
Damping arises as a result of air friction, as a result of friction in the suspension point. Two main sources, which we have ignored here.
Okay.
See, what happens in damping is that, in damping, for example, if I have a system where there is a damping present, so that equation of motion will contain another term here, bv square. If I throw a ball, it experiences air friction. If something is falling through the atmosphere, आपने class 11th या 12th में पढ़ा होगा, that it reaches terminal velocity. Why? Because even though it is accelerating forward, there is a friction due to air resistance. So whenever damping is present, the equation of motion gets modified and there is an additional term, either bv square or rho v, something like that, depending upon the nature of the damping. तो उसकी वजह से it does not remain as SHM anymore. It becomes what is called What is called a damped oscillator. Damped oscillator आप लोगों ने पढ़ा होगा ना. Damped oscillator में क्या होता है?
So
ये
the
हो जाता है.
amplitude gradually decreases.
Yes. So that is the, so you study this in wave optics. So you will study it in wave optics. Possibly अपने college में भी पढ़ा ही होगा. There is something called damped oscillator. There is something called critical damping. There is something called over damping. So they all arise in non-ideal situations. So right now I'm studying like an ideal system. But if you study non-ideal realistic situations, you will always have to include damping. After a couple of lectures, we will do some problems related to damping because mechanics में भी damping damping related questions होते हैं. And I'll show you how to do questions involving damping. Right now we are doing ideal systems, no damping, just pure forces. Okay. All right. Akash sir, इसमें cos omega t plus phi, phi किसको represent कर रहा है? Phi is a phase difference. It depends upon the time axis. टाइम एक्सिस के ऊपर डिपेंड करता है. देखिए, अगर आपके पास कोई सेकेंड ऑर्डर डिफरेंशियल इक्वेशन होता है तो आपको पता होगा कि जो सॉल्यूशन में दो कांस्टेंट्स होते हैं. तो यहाँ पे हमारे पास ये दो कांस्टेंट है. अगर मैं दोनों को कंबाइन कर दूं तो ये दो कांस्टेंट आ जाता है. तो व्हाट इज द फाई? फाई गिव्स यू एन आइडिया अबाउट फेज डिफरेंस. फॉर एग्जांपल, व्हाट इज द डिफरेंस बिटवीन दिस कर्व एंड दिस कर्व? बताइए. बोथ हैव द सेम एम्पलीट्यूड, बोथ हैव द सेम फ्रीक्वेंसी. व्हाट इज द डिफरेंस between both these? Phase difference. So that is the phase difference. Okay, that gives you the phase of the wave. All right, let's move forward. I hope that this has given you some idea of how to do problems related to simple pendulum and circular motion. One more case study. ठीक है. देखिए, what I am doing right now is nobody is going to ask you these case studies directly in the exam. My only purpose is that you understand the nature of how the calculations work, so that you can also implement these kinds of calculations later on in other problems. Okay, that's the whole purpose. Okay, so try to understand the mechanism which I'm following. Conical pendulum. Conical pendulum is a little bit different. Simple pendulum क्या होता है? The motion of a simple pendulum is restricted to a plane. Conical pendulum होता है when a bob is suspended from a ceiling using a string, but the motion is not constrained to a plane. The motion is along the cone. आप लोगों ने बचपन में साइंस म्यूजियम कभी गए होंगे, राइट? बचपन में साइंस म्यूजियम जाते हैं स्कूल की तरफ से बच्चे. तो साइंस म्यूजियम जाने के टाइम पे आप लोगों ने देखा होगा समथिंग कॉल्ड अ फोकल पेंडुलम. देखा है किसी ने?
Yes, sir.
व्हाट इज द फोकल पेंडुलम? म्यूजियम में देखा होगा, ऐसे घूमता रहता है, एक लंबा सा पेंडुलम होता है, ऐसे घूमता रहता है, ऐसे करके ऐसे करके. And using the focal pendulum, you can get some idea about the rotation of the earth. So the focal pendulum is a conical pendulum. Let's understand the conical pendulum. The interesting thing about the conical pendulum is that it is not moving on a plane, it is moving on the 3D space. So it is creating, or it is tracing out the base of a cone. It is tracing out the base of a cone. Okay, so let's suppose that the motion is happening like this. Okay, let's suppose this is the length L. All right, this is the bob. What are the various forces involved? What are the various forces involved? बताइए. What are the various forces involved here?
mg, tension.
You have mg acting downwards. You have the tension acting along the string. अब यहाँ पे देखिए, in the case of the simple pendulum, For me to resolve the various forces, I chose a coordinate system. The coordinate system has r cap and theta cap. And the origin of the coordinate system is this. The suspension point is the origin of the coordinate system. अब ये देख के मुझे बताइए, if I choose polar coordinates, then what should be the origin of the coordinate system?
The center of the path.
Center of the path. Very good. Center of the path. Okay, not the suspension point. Center of the path. Why? Because we are interested in the trajectory. And the trajectory is on a plane. And I want to take the center of that plane to be the origin. Yeah. So if I choose the center of the plane or the center of the path on which the to be the origin, then what is the radial direction? The radial direction is this. ये है कि नहीं? पेंडुलम से थोड़ा अलग है. This is the radial direction. Yes or no? बताइए, clear है? This is the radial direction. Yes?
Yes, sir.
Yes. Now, in which direction theta is increasing? Theta is increasing in this direction, right? इस डायरेक्शन में थीटा बढ़ रहा है, तो इसमें थोड़ा ड्रॉ करना मुश्किल है, बट मैं इसको ड्रॉ कर देता हूं. दिस टेंजेंट, ये, दिस इज द एंगुलर डायरेक्शन. बेसिकली दिस इज परपेंडिकुलर टू माय स्क्रीन. दिस इज परपेंडिकुलर टू माय स्क्रीन, बट मैंने इसको ऐसे ड्रॉ कर दिया. ठीक है, परपेंडिकुलर. mg और फाई कैप के बीच में 90 डिग्री है. mg और फाई कैप के बीच में 90 डिग्री है. ऑलराइट, क्लियर है. नाउ, so what is the radius of this? The radius of this is basically, if I consider this to be theta. Now यहाँ पे एक और चीज आ जाता है. There is one more angle which is involved in this problem, and because we are dealing with a 3D problem, there is an angle of inclination with the suspension point. This has nothing to do with theta. This is different. इसको मैं phi बोल देता हूँ. ठीक है, but it is equally important because it gives us an idea about equilibrium. Okay, phi and theta are not the same. So now if I want to resolve the forces, let me resolve the forces in various directions. So mg need not be resolved. This I can resolve as t cos phi this I can resolve as t sin phi और कुछ t cos phi t sin phi resolve कर दिया, काफी है. All right, काफी है. I have done everything. Now let us study this problem. First of all, if I look at the radial, इसको मैं L बोल देता हूं. Radial distance. What is the radial distance? Radial distance क्या है? L sin phi. Yes or no? L sin phi is the radial distance. Yes or no?
Yes, sir.
क्योंकि we have chosen the origin of the trajectory to be the center of the coordinate system. So r is equal to L sin phi. This. ठीक है. Now यहाँ पे दो तीन चीजें हैं. Couple of things involved. The pendulum could be going on in like a complicated trajectory. धीरे धीरे phi might decrease, or it could be in some kind of a vertical equilibrium. So that's a easy case study. तो मैं vertical equilibrium को study करता हूँ. Vertical equilibrium का मतलब क्या होता है? Vertical equilibrium का मतलब होता है phi is a constant. Phi is a constant. मतलब essentially the height of the conical pendulum is a constant for whatever reason. ठीक है ना? Ideal system phi is a constant. तो अगर phi is a constant होगा तो automatically r dot is equal to r double dot is equal to 0. Number one. Now, along I can look at the transverse direction first. Along transverse direction, what is the force equation? F theta is equal to m r theta double dot plus 2 r dot theta dot, but r dot is equal to 0, right? So therefore, this basically becomes, what is F theta, guys, from the diagram? What is F theta? What is F theta?
Is not it 0?
It's 0. There is no force along the F theta, right? देखिए, थीटा की डायरेक्शन कोई फोर्स ही नहीं है, ठीक है ना? So this is equal to mr theta double dot, ठीक है? So that means theta double dot is equal to 0. That means theta dot, which is basically equal to omega, is equal to constant. So vertical equilibrium का मतलब है the angular frequency of these oscillations, omega, it is a constant of motion. जिसके साथ वो ऐसे जा रहा है वो constant है, ठीक है? Now let's look at along radial direction. What is along radial direction? So Fr is equal to m r double dot minus r double dot minus r theta dot square. So what is r double dot? 0. So what is the force along the radial direction?
T sin phi.
T sin phi? Are you sure?
Minus T sin phi.
Minus T sin phi. Minus T sin phi is equal to minus mr theta dot square. Therefore, this becomes minus T sin phi is equal to minus m, r is equal to L sin phi theta dot square. So this becomes sin phi gets cancelled, and you are left with T is equal to m L theta dot square, which is also equal to ml omega square. That's it. Omega is a constant, so tension is a constant. Okay? So these are the two equations of motion for a conical pendulum. Now, I did a special case for the conical pendulum. I considered vertical equilibrium. Vertical equilibrium matlab the vertical height is a constant of motion. So if the vertical height is a constant of motion, that means the forces along the vertical direction are also balanced. What are the forces along the vertical direction?
T cos theta and minus mg.
T cos phi.
Yes, cos
T
phi.
cos phi and mg. Okay. So I can include one more equation along vertical direction. Along vertical direction, I will include another. So T cos phi is equal to mg. T cos phi is equal to mg. Okay. From here, I can say that what is T? I can include T here. That ml omega square cos phi is equal to mg. So m and m gets cancelled, and cos phi is equal to g upon omega square L. This is called the condition of vertical equilibrium. So if it is in vertical equilibrium, then this condition will be satisfied. So the vertical angle as well as the angular frequency. There are many questions revolving around the concept of vertical equilibrium. All right. मैंने ये दोनों प्रॉब्लम डिटेल में आपके सामने करा है, so that you at least get an idea about how to go about solving a problem of circular motion and free body diagrams. There are many questions in the literature, but most of them they follow similar instructions or similar steps जो मैंने यहाँ पे follow किया है. बताइए कोई question है या can I give you some unknown problems? let me give you some questions to practice. Okay. All right. I hope you're writing everything down in notebooks. Please try this question. This is a question from TIFR 2015. आप खुद से एक बार try करो if you can solve it or not. Take out your, pen, pencil, notebook and try to solve this question. A particle slides on the inside surface of a frictionless cone. There is a particle which is sliding on the inside surface of a frictionless cone. The cone is fixed to this tip on the ground and the axis vertical as shown. The semi-vertex angle is alpha. If the particle moves in a circle of radius r0 without slipping downwards, what is the angular frequency of motion? Looks like a difficult problem. But if you have understood the instructions I have given in the previous problem, you can follow a similar steps. Take a few minutes, take 3 minutes and try this question.
Option A, master, is right.
Pardon?
Option A.
Write the answers in the chat so that I can confirm from there.
How could I chat the answers in
You are attending from laptop or mobile phone?
laptop, master?
So there is a chat option there in the laptop.
Yes.
Yeah, in the chat you can just type your option.
Thank you, master.
Only I will be able to see it and I can confirm from there. All right. Let us see. Bamdev, it is not correct. Rakesh, Vivek, correct answer. Ruchir, not correct. Prayog, not correct. Uttam, not correct. Gunalam, not correct. Don't worry about it. It's not that easy a problem. Param also not correct. Can we start? Let us start. All right. Right now, we are in the learning phase. So we are just trying to learn the method to solve the problem. Solving is the second part. Learning the method is important. What is the method? We write down all the forces properly. We choose the coordinate system properly. We resolve the forces along the various axes properly. Then we write down the force equations in various directions. And from the force equations, we try to get the answer. This is the instructions. So, first, what are the various forces involved here? Bataiye, what are the forces involved?
Normal reaction.
So, first is gravity, right?
Yes.
And then you have normal reaction. Why? Because the bead is sliding on a conical surface. So, of course, there is going to be a normal reaction. Now, I want to choose the origin of the coordinate system. Which one should I choose? Origin of the trajectory?
Yes.
Origin of the trajectory. Like this. All right. So, I want to resolve the normal reaction in various directions. So, this is the vertical. So, if I resolve the normal reaction, this is alpha, right? So therefore this is what is this? N cos alpha, right? This is N cos alpha, right? And what is this force? N sin alpha. Okay. All right. Now let us look at the transverse direction first. What is the transverse direction? F theta is equal to M R theta double dot plus 2R dot theta dot. So the question is saying it doesn't slip downwards. Therefore, it moves in a circle of constant radius. So R naught is constant. Therefore, R dot is 0. What is the force in the transverse direction? बताइए. Trajectory के perpend transverse direction में क्या होगा? Force. मतलब coming out of the screen. What is the force coming out of the screen?
0.
0. So 0 is equal to M R theta double dot Therefore, theta double dot is equal to 0. Therefore, theta dot is equal to omega is equal to constant. Omega is also a constant. All right. Now, let us look at the radial direction. What is the radial direction force equation? The radial direction force equation is Fr is equal to m r double dot minus r theta dot square, but r double dot is equal to 0. But what is the force along the radial direction? Force along the radial direction?
n cos alpha.
दोबारा से पूछता हूँ. Force along the radial direction?
minus n
Minus
को
minus n cos.
Minus n cos alpha. Minus n cos alpha is equal to minus mr omega square. ठीक है? So therefore, n cos alpha is equal to mr omega square. Now, in questions like these, there is one additional condition. क्यों? Because without slipping, constant radius में move कर रहा है, मतलब vertical equilibrium का condition आ गया इसमें. मतलब vertically it is at a constant height. So in vertical equilibrium condition, you have n sine alpha is equal to mg. Right? So I have this equation, and I have this equation. So now I can combine using 1 upon 2. So what is n sine alpha upon n cos alpha equal to? It is equal to n sine alpha is mg, m cos alpha is mr omega square. N and n gets cancelled, m and m gets cancelled, and therefore you have tan alpha is equal to g upon r omega square. क्वेश्चन में हमसे पूछा गया omega is equal to g upon, so radius is constant, so r naught substitute कर देते हैं, r naught tan alpha root over. The correct answer is option number D, root over g upon r naught tan alpha. This is the correct option. बताइए, where did you guys make mistakes? मतलब कहाँ पे आपका calculation यहाँ से अलग है? At what stage? Most of you got option number C. So like where, at what point you made a different calculation? Don't worry about it. We can brainstorm the errors. Param, Bamdev, like at what point did you make a different kind of a calculation?
So during this after the omega square, I just revert the tan alpha, then it got cot alpha mistakenly. Means omega square is equal to g by cot alpha. I did it like this.
Oh, instead of cos, you wrote cot.
Yes, sir. In
Okay.
this particular case.
Okay, understood. Prayog, we will get C if we play around with conical calculation. What do you mean, Prayog?
Sir, I just resubstituted for omega for the expressions we got for conical pendulum, and we'll get cot alpha in that case for omega.
But it's not a conical pendulum, right?
Yes, sir. It's like a inverted.
It's a bead sliding on a conical surface. So in the conical pendulum, the calculations, so in the conical pendulum, the mg is this side. But in this problem, the mg is towards this point. You see? In the conical pendulum, the mg is away from the suspension point, gravity. But here it is away, it is towards, so you can't substitute that same
Yes.
formula. Are you understanding?
Yes, sir.
It's a different configuration, so you have to solve it from scratch. All right, guys, let's move forward. See, the point is not to actually solve this question. ये question तो TIFR में 2015 में आ चुका है. The point is to do similar questions, okay? By understanding the steps. So let's move forward to one more question. See, these TIFR questions are very interesting because they really challenge your concepts, whether you really understand the concepts or not. All right. So this is a question from JEST 2016. So a hoop समझते हो ना, जो सर्कस में सर्कुलर रिंग होता ना, ऐसे ऐसे घुमाते हैं बॉडी में, या ऐसे ऐसे जिम्नास्ट्स लोग यूज करते हैं hoop, circular hoop. A circular hoop rotates with a constant angular velocity omega about the vertical axis as shown in the figure. A bead of mass m slides on the hoop, slides back and forth without friction. If g is less than omega square a, at what angle? So this is the angle. I am giving you the information, okay? It's part of the question. What angle theta apart from 0 and pi is the bead stationary? Are you understanding? So as a circular hoop is rotating, the bead which can slide on the circular hoop is also rotating. But it is being said that if the bead has a constant height, that means there is vertical equilibrium, then what is the condition for the vertical equilibrium? Configuration is different, problem is similar. Give it a shot. Take 3-4 minutes. Try to solve this question. Everyone, try to solve this question. If you can solve these questions, then you will find similar problems easy to do later on, right? Bamdev, your answer is correct. Vivek, Rakesh, correct answer. Good. बाकी बच्चे भी ट्राई करो. सिमिलर सवाल है. सारे फोर्सेस को पहले तो ड्रॉ करो. Choose the right coordinate system. Resolve all the forces. Then write down the force equation. And then from there you will get the answer for vertical equilibrium.
May I ask you a question?
Yes.
In the conical pendulum, the motion of the pendulum is along a plane, but you have shown that it is along the circular path. But in the focal pendulum, I have seen that the pendulum motion is not along a circular path. It is like a this point to this point. It is like a zigzag circular path. It is not completely related. The motion actually, it's not completely. So how a focal pendulum is a type of canonical pendulum?
No, what I took was a special case. In general, the motion is not restricted to a circular path. That is a more complicated problem to solve. You will not get that problem. See, if you are looking at a general motion, then the height is not a constant. So it's not a vertical equilibrium. Are you understanding?
Okay.
So I took a special case. ये जो मैंने यहाँ पे लिखा था ना, ये जो मैंने vertical equilibrium लिया है, it's a special case to make the problem easier for me to demonstrate. So it's a special case. Special case of a vertical equilibrium. In like a focal pendulum, you don't have a special case. It's a general case. And not only you have a general case, you also have additional forces due to the rotation of the earth. So it's even much more complicated actually. So we are just trying to look at a very specific example when there is vertical equilibrium. And when I say vertical equilibrium, it means the forces in the vertical direction are balanced, as a result of which the height of the bob remains a constant, and that condition leads to omega is a constant, and if omega is a constant, you end up getting a circular path. ठीक है, तब आपको सर्कुलर पाथ मिलता है. जनरल केस में नहीं मिलेगा, लेकिन जनरल केस का प्रॉब्लम आपको मिलेगा भी नहीं, बिकॉज दैट्स quite difficult, because then you will have multiple differential equations to solve simultaneously. So those are difficult problems. You will not get it in the exam. If you get something in the exam, it will be similar to this, what we are doing right now, where you might have some kind of a vertical equilibrium or some condition like that.
Yes.
All right, anyone else? Come on. हम थोड़ा in the second, we have reached the second week, right? Third week, and already everything looks hard. कोई बात नहीं. If you deal with hard problems, then the easy problems are already taken care of. So these are hard problems, okay? Not everybody can solve these problems. Trust me. बहुत अच्छे स्टूडेंट्स, जी वगैरह के स्टूडेंट्स को भी मुश्किल लगेगा इस तरह के क्वेश्चंस. गेट वगैरह के स्टूडेंट्स को भी इस तरह के क्वेश्चंस मुश्किल लगेगा. दीज आर नॉट इजी प्रॉब्लम्स. Shall I start? Prayog, your answer is correct. मैं स्टार्ट कर देता हूं. I hope that you are able to understand the problem. It's a hoop. समझते हो ना? एक circular ring है. वो ring is rotating about the diameter. There's a circular ring. The ring is rotating about the diameter. Ring के ऊपर there is a bead. The bead can slide on the ring. But because the ring is rotating about a diameter, the bead is also moving along the ring. But if angle theta is constant, then what is the trajectory of the bead? बताइए. It will be circular. Yes. If angle theta is a constant, then the trajectory of the bead will be a circular trajectory. It's a special case, okay? It's not a general case. In a general case, the bead could be going about in any direction on the surface of a sphere. The bead could have some kind of a complicated trajectory on the surface of a sphere in a general case scenario. But we are not doing a general case scenario. We are doing a special case scenario in which the forces in the vertical direction are balanced so that the bead is only moving on a circular path fixed on a plane. हम सिर्फ उसको स्टडी कर रहे हैं. So what are the forces involved? Of course, the number one force is gravity, mg. Now, what else?
Normal reaction.
Yes. Now the normal reaction is not very obvious right now because you might say there is no surface here, but you can think of it like this. If the circular ring is oscillating or revolving about its diameter, then it is essentially tracing out a spherical surface, right? And the bead is always confined to the spherical surface. Bead is always confined to the spherical surface. As a result of which there has to be some kind of a normal force, because it is at the end of the day contact force, right? Normal force क्यों होता है? Because of a surface. Tension क्यों होता है? Because of some string. Right now we don't have a string, we don't even have a surface, we basically have a ring which is rotating about its diameter, but it is creating the same effect that the bead is constrained to move on the surface of a sphere. So if the bead is constrained to move on the surface of a sphere, we can imagine that there is a normal force that is constraining the bead to be on the surface of a sphere. So what would be the direction of that normal force? The direction of that normal force will be perpendicular to the tangent. So what is perpendicular to the tangent? Along the radius. Right. Now, because there is vertical equilibrium here, सबसे पहले what is the radial direction? Radial direction is this direction. Radius coming out of the center of the circular trajectory. The vertical direction is this. And let's suppose हमें theta जो दिया गया है, that theta is this. So what are the various forces involved? I can resolve the normal reaction and cos theta along this direction and sin theta along this direction. What are any other forces involved? No. So let us look at the radial direction. What is the radial direction? Fr is equal to MAR. So this is equal to M R double dot minus R theta dot square. What is R? R is equal to
A sin theta.
A sin theta. If theta is a constant, R double dot is equal to 0. Therefore, what is the radial force?
Minus n sin theta.
Yes, minus n sin theta is equal to minus M. R is equal to A sin theta, theta dot square. So sin theta cancel, minus minus cancel, n is equal to MA omega square. Theta dot is equal to omega. Okay. Now what if we look at vertical equilibrium? What is the forces? N cos theta is equal to mg. दो equation आ गई, equation number 1, equation number 2. Let's use equation number 1 and 2. So n upon n cos theta is equal to ma omega square upon mg. N and n gets cancelled, m and m gets cancelled, and you are left with cos theta is equal to g upon a omega square. This is the condition of vertical equilibrium. Answer is option number C. So easy. Such a small question. Just a couple of steps. But let me tell you, this is like a really hard question for somebody who is not used to these kinds of problems. जिस बच्चे ने इस तरह के क्वेश्चन पहले नहीं करे हैं, उसके लिए बहुत ही मुश्किल सवाल है. इतना आसान नहीं है. It's going to take a lot of time, lot of introspection. But otherwise, if you have done these kinds of questions before, then it becomes very easy. Right? All you have to do is write down the forces, resolve them into r direction, theta direction, vertical direction, and write down the relevant equations, force equations, और जो पूछा गया है उन इक्वेशन से उसका आंसर निकाल लो. Done. That's it. All right. चलिए आगे बढ़ते हैं. थोड़ा सा अलग टाइप का क्वेश्चन करने की कोशिश करते हैं. ठीक है ना. लेट अस डू सम लिटिल बिट ऑफ अ डिफरेंट टाइप ऑफ क्वेश्चन, है ना. All right, this is a practice problem for you. Interesting problem. Let's try to solve this. In the figure shown, a particle of mass m, this is a particle of mass m, is attached to a light string which moves on a smooth table with constant angular momentum L. I hope that you understand what an angular momentum is, even though मैंने अभी तक आपको बताया नहीं है, but I hope that you do know what an angular momentum is and maybe you'll be able to use it. The string passes through a hole on the table and a block of capital mass M hangs on it. ठीक है, ये mass. If r is the distance of small m from the hole at any instant of time t, then what is the acceleration of the capital mass m? समझ रहे हो क्या हो रहा है? कि मतलब एक टेबल है, टेबल में एक होल है यहां पे, और एक स्ट्रिंग से दो मासेस को बांध दिया गया है. One mass is going around in a circle on the table, that is creating some sort of a force, centrifugal force. Other mass is being pulled downwards. So what is the effective acceleration of the larger mass? Are you understanding? Question में हो क्या रहा है? String is passing through the table. The mass on the table is going around in some kind of a circular motion as a result of a constant angular momentum. But because that mass is attached to a lower mass, which is hanging downwards, which is trying to fall down, तो क्या होने वाला है? अगर ऊपर का मास बहुत ज्यादा फास्ट मूव करेगा तो नीचे का मास ऊपर चला जाएगा. अगर ऊपर का मास स्लोली मूव करेगा तो नीचे का मास नीचे की तरफ आ जाएगा. आई होप दैट यू आर एबल टू विजुअलाइज द मोशन. टेक योर टाइम, टेक 3-4 minutes एंड ट्राई टू सॉल्व दिस क्वेश्चन. ठीक है. अगेन, what are we supposed to do? Balance all kinds of forces. What is interesting is that in this system there are two particles involved, two particles interacting with each other. Look at all the force equations that are possible here, and from there come up with the answer. Angular momentum का formula पता है ना आप लोगों को, या मैं बता दूं? Do you know the formula for angular momentum? Guys, for a point mass moving in some kind of a plane, do you know the formula?
No, sir.
पता होगा यार, 12th में पढ़ा होगा.
अरे MVR
R cross
MVR
P.
मतलब MR स्क्वायर ओमेगा. MR स्क्वायर ओमेगा नहीं पढ़ा?
Yes sir, yes sir.
पढ़ा होगा यार, 12th में पढ़ा होगा. ठीक है, टेक इट एज अ हिंट. एम आर स्क्वायर ओमेगा, एम वी आर मतलब v इज इक्वल टू आर ओमेगा, तो एम आर स्क्वायर ओमेगा, जिसको आप एम वी आर भी लिख सकते हो, आपकी मर्जी है। Try this question, guys. Bamdev, your answer is not correct. Ruchi, I can't understand which option you're writing. बताइए। नहीं हो पा रहा? Where are you stuck? बताइए, we can discuss.
Sir, a few more minutes, please.
Okay. Bamdev, your answer now is correct. Very good. Rakesh, correct answer. Vivek, not correct. Uttam, not correct. All right, let me start. Okay, you cross check what's happening here. See, this is an interesting problem because here there are two kinds of motion that is happening. One is the motion of the small mass m on the table, and two is the motion of this lower mass. The second mass, the lower mass, is moving in a straight line. The first mass, the mass on the table, is moving in a circle. ठीक है? तो यहाँ पे XY कोऑर्डिनेट आ गया और यहाँ पे R थीटा कोऑर्डिनेट आ गया. तो दो तरीके का मोशन हो रहा है. Are you understanding? So on one hand, we have this kind of a circular motion happening. On the other hand, we have this kind of a vertical motion happening. And we can try to sort of look at both the circular as well as the vertical motion. Okay, try kare. So tell me something, guys. If I only look at the vertical motion, just look at the vertical motion. What are the forces involved in the vertical motion? Just tell me the forces.
Sir, mg and the tension of the strings T.
Yes, mg acting downwards and tension of the string acting upwards. But the moment I say tension is upwards, it means that there is also a tension here. Why? Because of interaction. When two masses are interacting with each other, they experience equal forces acting in opposite directions. Okay? Newton's third law. Ye bhi aa gaya. Now, I must choose a direction of acceleration. Do you want to choose downward acceleration or upward acceleration? Let us choose that the system is moving downwards. A. So if this system is moving downwards with A, ये mass भी radially नीचे आ रहा होगा A में. Yes or no?
Yes.
क्योंकि string is inextensible. So in vertical motion, F net is equal to capital MA. What is F net? F net is equal to ये capital M है, sorry. देखिए क्वेश्चन बहुत सिंपल है. आई एम जस्ट ट्राइंग टू ब्रेक डाउन द क्वेश्चन इनटू सिंपल concepts. I'm just looking at the vertical motion of the lower mass and the circular motion of the upper mass. That's it. And in the vertical motion of the lower mass, the net force is capital mg minus tension T, which is equal to capital Ma, जिसको मैं लिख देता हूं minus T is equal to कैपिटल M A माइनस G, ठीक है, ये मेरा इक्वेशन हो गया. ऑलराइट, नाउ let us look at the circular motion of the upper mass. Okay, we looked at the vertical motion of the lower mass. Now let us look at the circular motion of the upper mass. Now in the vertical motion, we can write this equation. Why? Because it's a vertical motion. We can think of this as the y-axis. But if we talk about circular motion, I need to use polar coordinates. So let me use FR. FR is equal to M R double dot minus R theta dot square. What is the force in the radial direction, guys?
Tension.
minus T.
Minus T, because tension is acting in the
Downward
decreasing radial direction.
decreasing.
Decreasing radial direction, right? Now, what is R double dot?
So minus A.
R double dot is minus A. R double dot is not just A, it's minus A. Why is it minus A? Because A is decreasing. ठीक है, यहाँ पे थोड़ा सा आपको ध्यान देना पड़ेगा. That is why the plus minuses are so important, because it affects your final calculations. R dot is decreasing according to my setup. मैंने बोला कि ये नीचे जा रहा है, अगर ये नीचे जाएगा तो ये भी अंदर की तरफ आएगा, तो डिक्रीज करेगा. R double dot is decreasing according to my setup. So therefore I am writing here minus A minus mr theta dot square. ठीक है, so this is equal to minus T is equal to ma minus mr theta dot square. That's it. Calculation बस इतना ही है. But 1 is equal to 2 कर देते हम.
सर
Minus T
माइनस
is-
है.
हाँ,
फिर वहाँ एक माइनस साइड ओमिट हो गया.
Minus MA.
minus ma. So this is equal to capital M A minus G is equal to small m A minus mr theta dot square. Now here what we can do is we can use this angular momentum expression. ठीक है, L is equal to mr square theta dot. I can use this expression here. So if I use this expression here, what is going to happen? Capital MA minus capital G is equal to minus small ma minus m r theta dot is equal to L upon mr square. So therefore capital Ma plus small ma is equal to capital Mg minus small m L square upon m r cube. mr cube होगा ना, हाँ mr cube हो जाएगा. So therefore finally it becomes A is equal to capital Mg minus L square upon mr cube upon capital M plus small m. That's it. This is your answer. Capital Mg minus L square upon mr cube divided by capital M plus small m. Answer is option number D. Now look at this, guys. This is very small amount of calculation. The amount of calculation is very less, because later on you will see that in questions involving electromagnetic theory, in questions involving modern physics, there are lengthy calculations, you know. Sometimes you need to solve a question for so long. But right now, the length of the calculations is very small. The only thing is that it is deeply conceptual. You need to understand the problem. You need to break down the problem into all the components. Circular motion को हमने देख लिया, vertical motion को देख लिया. Circular motion के लिए I wrote down the force equation along radial direction. Vertical motion के लिए I wrote down the force equation for the linear motion. From there I connected two dots. Angular momentum को substitute किया, I got the answer. So mechanics में always try to follow steps. If you do one step, second step, third step, you get the answer. Every difficult problem can be broken down into small steps, and as long as you follow these steps properly, you will finally get the answer. Okay, थोड़ा सा टाइम ज़्यादा नहीं है हमारे पास. Let us do a hard problem. All right, एक hard problem करते हैं. जो जैम में आया हुआ है. ओके, जैम का प्रॉब्लम करते हैं. दिस इज अ क्वेश्चन इन जैम. ऑलराइट, लेट्स मूव फॉरवर्ड. This is a question of JAM 2022, I guess, or something like that. Okay. Last problem of the day. If you can, solve it. A simple pendulum consisting of a point mass small m tied to a massless string of length L executes small oscillations of frequency omega and amplitude A is equal to L theta dot. The average tension of the string is what? They are asking you the average tension. ठीक है, बहुत ही इंटरेस्टिंग सवाल है. हमने यहाँ पे क्या करा था? In this problem, we calculated the instantaneous tension. मैं हिंट दे रहा हूं आपको. We calculated the instantaneous tension. But in this question, in the JAM question, by the way, JAM question hai, they're asking you the average tension. Think about it. Take a few minutes, take 3 minutes, solve this problem because it's a JAM question. Try. Come on, last question of the day. Do not lose hope. I know that these questions are a little challenging and थोड़ा सा नहीं सॉल्व होता है तो you feel demotivated. You feel like अरे यार इतने hard problems कैसे होगा, क्या होगा. Don't worry about it. It is just a class. ठीक है, I am just trying to make you familiar with the steps of tackling certain kinds of questions. ठीक है, कॉन्फिडेंस धीरे धीरे आएगा when you solve more and more problems. You know, you look at PYQs, you look at assignments, you'll try to solve them. बट उनको सॉल्व करने के टाइम पे आपको याद आएगा, अच्छा हमने क्लास में इस तरह से करा था, वी डिड इट दिस वे इन द क्लास, एंड देन यू विल ट्राई दोज same steps in those questions, and then you will gain confidence. Mechanics can be a little bit brutal in that sense, you know, even if you know the subject, you are unable to solve it, so it feels very frustrating. Don't worry about it. We're just practicing to understand the subject, because that's the only way to learn mechanics. Practice, understand. More practice, better understanding, like that. So in this question, it is not really that difficult because I have already calculated the tension in a string, but I calculated the instantaneous tension in a string at any random position. The question is asking you the average. You understand average, right? If I give you some function, if I give you some expression, you know how to calculate average, right? So you just have to calculate average of this problem. Average of the tension. That's it. फॉर्मूला ऑफ एवरेज टेंशन, देखो मैंने फॉर्मूला ऑफ टेंशन दे दिया है, अब आप एवरेज निकालो। टेंशन का फॉर्मूला तो मैंने दे दिया ना आपको, आप उसका एवरेज निकालो ना, ट्राई करो। और शैल आई स्टार्ट, मैं स्टार्ट कर दूं, बिकॉज ये थोड़ा सा हार्ड तो है, मतलब इट्स नॉट दैट इजी। शैल आई स्टार्ट गाइस? Okay, so can I use the expressions I already derived in the very beginning of the class? Can I use the expressions? Shall I use this expression? Will you be able to understand if I just use this expression? Bataiye. Is it okay if I use the tension expression without explaining how we got the tension expression? Because
Yes,
if you okay, so usually in the problem in an examination, if you do not remember the tension expression, you will have to draw the diagram, you'll have to write down the various forces, you'll have to write down the radial force equation, वहां से आपको टेंशन का एक्सप्रेशन मिल जाएगा। बट क्योंकि मैं ऑलरेडी आपके साथ टेंशन का एक्सप्रेशन कर चुका हूं, तो therefore आई एम गोइंग टू यूज द सेम हियर। सो फ्रॉम earlier calculations, what is tension? T is equal to mg cos theta plus ml theta dot square. This is the tension. आपको याद रखने की जरूरत नहीं है, आप याद नहीं रखोगे तो you will have to derive it, which is not really that difficult. You just draw the force equation, write down the radial direction force equation, and from there you can easily obtain the tension of a pendulum. There are questions in the literature where they are going to ask you find out the tension of a pendulum, or you might have to use the tension of a pendulum in some equation. So you can automatically derive it in rough, like in 20 seconds, not a big problem, okay? And what is the general solution for theta? Like a particular solution क्या मैंने obtain किया था, is equal to, initially क्या था, theta dot था ना, यहाँ पे amplitude theta dot है, theta dot is equal to amplitude, this is theta dot cos omega t, है ना? Yes, I'm going to use these two expressions. All right. Now, जब मैंने टेंशन निकाला था तो उस टाइम पे मैंने स्मॉल ऑसिलेशन नहीं लगाया, बट मैं अगर टेंशन में स्मॉल ऑसिलेशन लगा दूं, व्हाट इज द कंडीशन ऑफ स्मॉल ऑसिलेशंस?
Cos theta will become 1.
All right, this is a little tricky here. See, small angles में क्या होता है कि sin theta is equal to theta, but what is cos theta? That is a question. Now, if you reach the end of a solution, then you can write cos theta is equal to 1. But if you are at the beginning of a problem, you don't write cos theta is equal to 1. You write cos theta is equal to 1 minus theta square upon 2. You include the second term of the Taylor series expansion. Every series can be expanded, like, right, in an infinite series. So when I do sin theta, I take the first term of an infinite series. But when I do cos theta, depend करता है. अगर मैंने सारा कैलकुलेशन करने के बाद फाइनली मुझे cos theta मिला, तो मैं उसको 1 पुट कर सकता हूँ. लेकिन ज्यादातर मैकेनिक्स के प्रॉब्लम्स में ये होगा कि अगर मैं इनिशियली cos theta ले रहा हूँ, तो इट्स बेटर नॉट टू टेक 1. प्रॉब्लम क्या पता, 1 लेने से बिग कांस्टेंट बन जाता है, तो हमको वेरिएशन दिखता नहीं है. वी डोंट सी द वेरिएशन, इट जस्ट बिकम्स अ कांस्टेंट. ठीक है, ये चीज याद रखना. अब ये थोड़ा सा इंपॉर्टेंट है, क्योंकि मेजॉरिटी मैकेनिक्स प्रॉब्लम्स में इनिशियली वी टेक cos theta. अगर इनिशियली हम ले रहे हैं assumption, तो देन इट इज 1, वी टेक फर्स्ट 2 टर्म्स 1 minus theta square by 2. ओके, and what is theta dot? Theta dot is equal to minus theta naught sin omega t. तो यहाँ पे ओमेगा आ जाएगा ना. लास्ट क्वेश्चन है गाइस, ठीक है, जस्ट होल्ड ऑन, मैं 5 मिनट के अंदर खत्म कर देता हूँ इसको. सो दिस बिकम्स प्लस ml माइनस थीटा नॉट ओमेगा sin omega t square. So this becomes mg minus half mg theta square plus ml theta naught square omega square sin square omega t. ओके, क्वेश्चन ने पूछा क्या है? एवरेज टेंशन. सो व्हाट इज द एवरेज टेंशन ऑफ अ कांस्टेंट? इट इज अ कांस्टेंट. तो यहां पे मैं क्या लिख सकता हूं? हाफ एम जी. थीटा कैन बी रिटन एज फ्रॉम हियर थीटा नॉट स्क्वायर cos omega t average plus ml theta naught square omega square sin square omega t average. समझ रहे हो what's happening? I have converted the problem of average tension to finding out the average of cos and sin. आप लोग को cos और sin का average मालूम है? What is the average of sin square theta, sin theta? बताइए.
Half, I guess, for sin square theta.
ओवर अ फुल साइकिल बोला है ना यहाँ पे. t इज इक्वल टू 2 पाई होने में.
cosine 0.
ओके, एक एक करके करते हैं. व्हाट इज द एवरेज ऑफ साइन? इट इज साइन ओमेगा टी डी टी फ्रॉम 0 टू कैपिटल टी अपॉन 1 बाई टी. ये क्या होता है? एनीबडी नोस?
Sir, 0.
0 होता है बिकॉज प्लस माइनस दोनों मिला के हो गया 0. बट इफ आई टेक साइन स्क्वायर ओमेगा टी, एनीबडी नोज द एवरेज ऑफ दिस?
1 by 2.
Half.
1 by 2.
Because sine square is a different graph. Sine square is this. This is sine square. It cannot be 0. This is 1 by 2. Very good. Same for cos. Cos omega t average
0.
0 to t. Cos omega t dt is equal to 0. And cos square omega t average half. Done. कुछ करना नहीं था एक्चुअली. ये इतना मुश्किल सवाल नहीं है, बट थोड़ा बिकॉज ऑफ दिस एक्सप्रेशन ये मुश्किल हो गया. सो जस्ट वी सब्स्टिट्यूटेड एम जी माइनस हाफ एम जी, एंड दे आर सेइंग व्हाट इज ए इज इक्वल टू एल थीटा नॉट. दे हैव गिवन अस ए इज इक्वल टू एल थीटा नॉट. सो आई एम गोइंग टू राइट थीटा नॉट इज इक्वल टू ए अपॉन एल स्क्वायर. कॉस स्क्वायर ओमेगा टी इज हाफ plus ml theta naught is equal to a upon l whole square omega square times half. So this becomes mg minus 1 by 4 mg a square upon L square plus 1 by 2 m omega square a square upon L square. What is omega, guys, here? यहाँ पे ओमेगा क्या है? ओमेगा स्क्वायर इज इक्वल टू जी अपॉन एल, है ना? याद होगा आप लोगों को. सो ओमेगा स्क्वायर इज इक्वल टू जी अपॉन एल. कहीं पे सब्स्टिट्यूशन होगा ना, एक ओमेगा स्क्वायर जी अपॉन एल. जी अपॉन एल क्यू हो जाएगा क्या? अच्छा नहीं, सॉरी, यहाँ पे एल हो जाएगा. ठीक है. सो देयरफॉर दिस इज इक्वल टू एम जी माइनस 1 by 4 m g a square upon L square plus half m omega square is equal to g upon L and a square upon L. तो g upon L square हो गया. So therefore the final answer is mg minus half minus 1 by 4.
mg plus 1 by 4 m.
प्लस कैसे हुआ?
सर
Yes,
हाफ
फाइनल
ना.
फाइनल आंसर.
हाँ सर.
फाइनल आंसर इज mg a square upon L. ये होगा ना 1 by 4.
L
mg plus 1
square.
by 4 L square. तो g अपॉन एल स्क्वायर इज इक्वल टू ओमेगा एल भी लिख सकते हैं. अच्छा, ओमेगा के टर्म्स पे दिया हुआ है तो g अपॉन एल स्क्वायर को हम लिख सकते हैं. सो ओमेगा स्क्वायर इज इक्वल टू g अपॉन एल. सो दिस इज mg प्लस 1 by 4 g इज इक्वल टू ओमेगा स्क्वायर एल. सो ओमेगा स्क्वायर m ओमेगा स्क्वायर a स्क्वायर अपॉन एल. सो दिस आंसर इज mg plus m a square omega square upon 4l. a square omega square upon 4l. ऑप्शन नंबर ए. सो ये जो क्वेश्चन है ना, ये डिफिकल्ट इसलिए था बिकॉज यहाँ पे मैंने एवरेज का फॉर्मूला लगा दिया. अदरवाइज ये डिफिकल्ट नहीं था बिकॉज हमें टेंशन पहले से मालूम है. आई हैव ऑलरेडी टॉट यू हाउ टू कैलकुलेट टेंशन. द ओनली थिंग आई हैड टू डू वाज फाइंड आउट द एवरेज एक्सप्रेशन आफ्टर स्मॉल ऑसिलेशंस. So mechanics as well as physics, matlab if you see like any kinds of problems in JAM as well as TIFR or JEST, essentially it boils down to your capacity of connecting dots. ठीक है, चीजों को कनेक्ट करना होता है. It's a game, you know. If you are able to break down a problem into multiple steps and if you are able to connect the steps together, टेंशन का एक्सप्रेशन मैंने कैलकुलेट किया, स्मॉल ऑसिलेशंस का मैंने एक्सप्रेशन लगा दिया, एवरेज ऑफ सर्टेन फंक्शंस मुझे पता है, तीनों चीजों को आपने कनेक्ट करा, डन, यू गेट द आंसर. सो अल्टीमेटली it all boils down to your capacity of breaking a complicated problem into small steps and connecting those steps to get the final answer. So it's a very beautiful process. If you get comfortable with this process, you will get really good at various kinds of problem solving challenges. ठीक है, चलिए guys, I will give you some problems, homework problems. I won't come back to this topic of circular motion again. In the next class, I will go into kinematics of, you know, linear motion as well as kinematics of circular motion. ठीक है, तब हम discuss करेंगे. We will discuss further. That's it. Thank you so much. Tomorrow you have a mathematical physics class taken by Sagar sir. And yeah, I'll come back again. Yeah.
Sir, the difficult part was also figuring out that cos theta is equals to 1 minus theta square by 2. Sir, is this very often in calculation?
Yes, see, I will give you a general rule. The general rule is very simple, that if you want to apply small angle oscillation at the very end, then you can apply cos theta is equal to 1. But if you do it at the very beginning, then you take 1 minus theta square by 2. क्यों? क्योंकि कैलकुलेशन में ना 1 जो कांस्टेंट होता है ना, बहुत बार वैनिश हो जाता है. फॉर एग्जाम्पल यहाँ पे डिफरेंशियल इक्वेशंस नहीं है, बट व्हाट इफ आई हैड टू टेक सम डेरिवेटिव समवेयर. इफ आई टेक अ डेरिवेटिव, 1 will automatically vanish.
Yes.
So you will not be able to see a clearer picture with 1. 1 minus theta square by 2 is a much better function to approximate cos theta. Are you understanding?
Yes, sir.
So if you have to introduce cos theta approximation initially, you always take 1 minus theta square by 2. But if you have to introduce it at a later stage to get a final answer, then you can do 1. ठीक है, तो ये आपको मिलता है बहुत बार, स्पेशली सिंपल पेंडुलम, डबल पेंडुलम, ट्रिपल पेंडुलम कैलकुलेशंस में ना cos थीटा अप्रोक्सीमेशन आपको दिखेगा. एंड हमें लगता है कि 1 लेंगे तो ईजी हो जाएगा, बट दैट एक्चुअली वी आर नॉट एबल टू सी द रिलेशनशिप प्रॉपरली, सो यू डोंट गेट द फाइनल आंसर इन अ वेरी प्रॉपर वे. ये सारा कुछ ही वैनिश हो जाएगा अगर मैं cos थीटा 1 ले लूंगा ना. ये वाला टर्म, सेकेंड टर्म मेरे को मिलेगा ही नहीं, सेकेंड टर्म वैनिश हो जाएगा एक तरीके से. या दैट्स द थिंग. ऑलराइट, चलिए गाइस.
I have few question, may I ask?
या प्लीज.
Yes, sir. Sir, I am getting confused about the direction of the theta cap, transverse direction. How to choose the direction of the theta cap properly? Because I know that it is perpendicular to r cap, but often the diagram does not show the in which way the theta is increasing. So in that case, which will be my theta cap direction?
You choose the trajectory. So
I
for
can-
example, like if I choose here, I have drawn these arrows, right? You see the trajectory?
Yes, sir.
According to these arrows, theta cap is already decided. It is inside, it is in this direction. As the particle is moving forward, theta is increasing in that direction.
I can choose it as I wish.
Yeah. You just have to be consistent across your calculation. That's all.
In the case of simple pendulum, I can choose theta as I please. Means that is also fine, like.
See, if you want to choose this as theta, you can choose, but your equations will change.
Okay.
Your calculations will change. You can choose it, but your calculations will change. So the only thing is you need to be consistent with your calculations. समझ रहे हो? मैंने जो कैलकुलेशन करा है वो मैंने जो सेटअप बनाया है उसके ऊपर है. Now there is no absolute requirement कि this is what I am going to decide to be theta. ऐसा कोई absolute requirement नहीं है. थीटा में ये भी चूज कर सकता था, बट एक कन्वेंशन बन गया है. लेकिन प्रॉब्लम सॉल्विंग में कन्वेंशन फॉलो नहीं, प्रॉब्लम सॉल्विंग में कुछ भी हो सकता है. तो द ओनली थिंग इज दैट you choose something that is convenient and do the calculations accordingly, and then finally you will come up with some kind of an answer. And usually it should not make a difference. As long as you are consistent in your calculations, it should not make a difference. Here I have chosen with the vertical, so increasing theta is in this direction. तो थीटा कैप उधर हो गया, समझ रहे हो?
Okay.
लेकिन अगर पार्टिकल इधर होता तो थीटा कैप किधर होता बताओ?
The theta cap will be in the opposite
in
direction.
this direction, क्योंकि थीटा इधर बढ़ रहा है. That's all you have to make sure. The theta is increasing in the positive axis, decreasing in the negative axis. R is increasing in the positive axis, decreasing in the negative axis. That's all.
But sir, in this case also that the theta direction may vary. It depends on it has reached the maximum point or it is not. If it is
No. Even if the particle is moving downward, theta direction is always that side. Think about it. Even if the particle is, let's suppose particle इधर आ रहा है, ठीक है? Let's consider pendulum is coming this side, okay? Then also theta cap is in that direction, because it is only in that direction theta is increasing. The coordinate theta increases in that direction.
Oh, I get it.
It has nothing to do with the particle's motion. It has to do with your geometrical coordinate system that you have chosen. Okay? Particle के motion के ऊपर नहीं है ये.
In the equation, and another question, in the equation number 1, if generally if the t suddenly vanishes, the particle will follow a straight line. So how can I express that thing from the equation number 1? Because t will be 0. So after that, can this expression,
What do you mean straight line? It will become depends upon various
if I
factors.
suddenly cut the string, the particle will follow the straight line equation. So can I show this from the
No, there is
from-
gravity. Why will it follow straight line?
not for this case? Means if I
In the absence of gravity.
yeah.
In the absence of gravity, आपके पास ये term होगा ही नहीं फिर.
So it will follow the straight line. So can I express this from this equation number 1? The particle will follow a straight line. Can I show this from this equation, or it will be another equation?
No, this equation is only relevant when there is a string and there is a circular motion. The moment you cut the string, there is no circular motion. There is no tension.
Okay.
T is equal to 0. So mv, this is also equal to 0. तो ये पूरा 0 ही हो गया ना एक तरीके से. तो Newton's first law comes into picture. What is Newton's first law? कि the moment you cut the string, this equation stops making sense. So जो instantaneous velocity है, उसी velocity के साथ वो आगे बढ़ता रहेगा. Newton's first law takes its place. There is no force. In the absence of force, what happens? Constant velocity. बस, that's it. जो भी velocity की direction है, at the moment you cut the string, वो ही रहेगा. Newton's first law will take over in the absence of forces. Okay.
Another question that in the, can you show the picture about the hoop, about the question about the hoop?
Yes.
So here the question is saying that apart from 0 and pi, the beat is stationary. That it makes sense that if theta is equal to 0, the beat will be stationary. But if theta is equal to pi, how the beat will be stationary?
It can be stationary. It's a potential maxima. Potential maxima. Can the pendulum exist in this position? If all the forces are balanced? Yes, it can. Do you know that pendulum has two equilibrium points? This is one equilibrium position. This is another equilibrium position. But one is a stable equilibrium, the other is an unstable equilibrium. Have you studied stable and unstable equilibrium?
Yes, I have studied.
Yeah, we will do potential energy analysis. So there, if you draw a potential energy graph, then you will get a maxima and a minima. So minima is a stable equilibrium, maxima is a unstable equilibrium. So here, theta is equal to 0 is a stable equilibrium, theta is equal to pi is an unstable equilibrium. So in theta is equal to pi, what is going to happen is there are no forces, zero force. But it's an unstable equilibrium because if I do a little perturbation, it will fall down. It's like that. So both 0 and pi are equilibrium. So it will be a stationary situation, but one is stable, the other is unstable. But इस question में ये है कि apart from these two, there is one more point. That's the question here.
The last question. You have said that the harmonic thing have to be sinusoidal. So does it follow the Hooke's law or is not? Doesn't.
Any harmonic oscillator follows Hooke's law. All harmonic oscillators.
How can that be related about the sinusoidal thing?
It is related. We will study SHM if you want. So what is the definition of Hooke's law? The force is directly proportional to the displacement, but the direction is inverse. यही तो है Hooke's law. If you calculate potential, it comes out to be half kx square. Yes or no?
Yes, sir.
If you solve the force equation, it comes out to be x is equal to x naught cos omega t. If you draw the potential energy graph, it will be a parabola. ये सारा मैं SHM के चैप्टर में डिस्कस करूंगा. They are all connected to one another. They are all connected. I will derive it in the SHM chapter. ठीक है. वैसे वेव ऑप्टिक्स में भी डिस्कस होता है, बट मैं भी करा दूंगा एक बार. एक क्लास तो मैं भी लूंगा इसका. ठीक है. All right.
Thank you.
All right, guys. Thank you so much. Have a nice evening. Good night.
Thank you so much.
Bye.